very, very, very important lesson is coming down the pike today, okay? It not only is going to use some of those warm-up questions that we looked at yesterday where we solved quadratic equations and we simplified radical expressions, but we're going to put it into the context of triangles and working with some triangles. I've got on the screen right now, as a matter of fact, the theorem itself that we mentioned yesterday in red, and then we talked about the converse in green. The converse is just the reverse, the different direction. Instead of saying if you got a right triangle, then you've got the relationship between A, B, and C. The converse says if you know this relationship between these three numbers exists, then you got a right triangle using those three numbers. Do you have to have A, B, and C, or can Pythagoras apply to any letters? It can apply to any letters, okay? The 8th graders were first learning about this morning, just a bit ago, and somebody said, does A and B and C have to be in that order? Could I use A and B and C in a different order? And you totally could. Like, for example, we might say in Algebra 2, as a matter of fact, you guys will see, you'll learn about the shape called the ellipse where B and C and A are located in those places, right? Where B and C are the legs and A is the hypotenuse. If that were the case, what would the theorem's conclusion be? Yeah, very good. The two legs still get squared, and that sets equal to, when you add them together, the hypotenuse squared. It's just a different ordering of the letters. Now, it would be foolish for me to teach a class of freshmen to memorize the Pythagorean theorem as b squared plus c squared equals a squared, but it's the theorem nonetheless. It's the sum of the square of the legs of a right triangle equals the square of the hypotenuse. Whatever you call those legs and hypotenuse is up to you, okay? Now, we're going to use, this is our very first example, we're going to use Pythagoras to solve for a missing side of a right triangle. This is one of the primary uses of Pythagoras, is to solve for a missing side of a right triangle, okay? So, draw out this triangle. I'm a very visual person. I always like to draw the picture out if I can. So draw yourself this right triangle out, and we'll see if Quinn can, now that we know this is a right triangle, see if Quinn can quote the theorem for us by plugging in those particular numbers and letters. Well done. Just as he said, we've got 3 squared plus x squared equals 5 squared. Now, Luke, what do you think logically would be the easiest thing to do next? Read what's in blue and just tell me what the first thing that comes to your head is. Absolutely. That's exactly what we should do. 3 squared is 9. I should write that down. X squared I can't do anything with. 5 squared is 25. I should write that down. That's the very first thing you should do. It's easy to do, and a lot of you guys can do that step in your head, right? Everybody knows what 3 squared is. Everybody knows what 5 squared is. So you don't have to write that step down, but you still need to square those. And then, JT, what would my next step be, given that I'm trying to get x by itself? Good. So I'm going to subtract 9 from both sides, and I'll get 16. And then, Justin, what's my next step? We don't want to divide because we're not multiplying.
You have to get back to the second power.
So, okay, good. You've identified this is raised to the second power. What undoes a square? Good. That's our inverse op, right? So this year we've learned, I think I've been counting, we've learned 4 pairs of inverse ops. We've used addition and subtraction, right? We said, since it's plus 9, let's minus 9. Justin mentioned multiply and divide. We are going to undo a square, we're going to make use of a square root. What's that newest pair of inverse operations that y'all learned about? Yeah, the logarithmic function, the exponential function. So those are our inverse ops so far. Now, Hogan, when I take the square root of both sides, what am I going to end up with? All right, let me ask you this, because you're not incorrect. I just want to adjust what you said just a little bit. What kind of equation is, or nay, let's back up to the beginning. What kind of equation is this? It's an x squared equation. We call that a what? It's not linear, it's...
My mind's slipping.
That's okay, we'll throw it to Calderoni. It's a quadratic equation, good. And William Bryan, how many solutions does a quadratic equation have? It has 2 solutions. Now, if I take the square root of both sides, Hogan has given me 1 solution. How can I help Hogan remember what the other solution will be? What do I always want to remember when I take the square root of both sides, Jacob? We're going to put on a plus or minus in front of that 4, all right? So now we've solved that equation. And some of y'all might be looking at me like I'm a crazy person. Because what does x stand for in this problem, in this context? The leg or the side of a triangle. Jackson's looking at me like, dude, you can't have a negative length on the side of a triangle. And he's very correct. -4 in this context, we would consider to be an extraneous solution. We would throw it out. We'd say, oh, that doesn't work. So just +4 is my answer. And I always like to write my answer up on the actual picture, right? X = 4. But did you know, and I bet you did because Mr. Niggles teaches some of y'all some chemistry, doesn't he? I mean, some physics, doesn't he? Did you know that you can connotate a number? Do we know the difference? See, I'm teaching you all kinds of, we're doing math, physics, and English today. What's the difference between a denotation and a connotation? Louder? By the way. Yeah, so denotation starts with the letter D, which dictionary starts with a D. So denotation is the dictionary definition of a word. And connotation would be kind of how we apply that word in perhaps a secondary context. Connotation, context, right? So did you know that in physics sometimes you can connotate a number with a negative sign in this kind of example? You could say, hey, maybe that triangle is moving 4 units in the negative direction, so we might say it has a negative. I do that all the time in my trigonometry class, right? So like I might say, hey, given that the cosine of theta equals -4/5 and theta is in quadrant 2, draw the picture out. Well, those guys have learned that -4/5, there's theta, and then they operate with it accordingly. So they literally say that the side of a triangle isn't negative, but it's moving in the negative direction. So we can be comfy knowing that a quadratic equation, which William's correct, has 2 solutions. We are only going to use the positive solution in this context because it wouldn't make sense. But perhaps like in orange, in some other contexts, it might make more sense to consider it negative. All right? You guys try one. And I'll zoom out enough to where you can see. All right, y'all try this one.
Do you ever need to know the negative like stuff like for algebra, regular algebra, or just like
Algebra 2 and stuff like that. Again, I'll encourage you to make the drawing, but you can make the drawing whatever way you want to make the drawing. And what I mean by that is you can reorient it, you can draw it differently as long as you maintain the relative positioning of those sides. So like I couldn't make the hypotenuse 5 all of a sudden, but I can certainly lay that triangle a different way if it helps. So mimic example 1. Set up an equation. Solve that equation. Label the picture. All right, Ashton, how about you lay on us the old equation for us, please?
5 squared plus y squared equals 13 squared.
Beautiful. All right. Now, do you guys remember earlier in the year where I encouraged you to like memorize your perfect squares 1 through 20? Okay, so like Nick Pesci, for instance, do you know what 13 squared is?
I'd say
Wilson, what do you think it is? 169. Good. That's all good. So that's a good illustration of, like, Nick could totally just sit and work out 13 times 13 and, you know, do the arithmetic. And there's nothing wrong with that. But if I've got it memorized, I'll move a little bit what? I'll move a little bit quicker. Okay. Now, we've plugged it into the formula. Very good job, Ashton. We said, you know, 1 leg squared plus 1 leg squared equals hypotenuse squared, even if this triangle was laid over onto its hypotenuse. All right, so William Kreitz, what's my next step? Good, so I get what? And therefore, y is going to equal what, class? Good, Hogan, attaboy, plus or minus 12. In which case we would just say, oh, well, y equals 12. That's my answer. Y equals 12. Because in this context, it wouldn't make sense for me to say, well, that side is negative 12. Because I'm not in the middle of, like, for example, a trigonometry problem. Okay? Wait. Great question. No, like if this was in exactly as it's written out, if this was an ACT, which, by the way, I posted one yesterday. Did you guys see that it posted?
Yeah.
Okay, perfect. Sometimes I worry that it doesn't post. I know what I need to do. Did I put it on y'all's assignment center? That's what I might not have done. I did? It's on there? Okay, good. All right, so anywho, to William's question, man, it would, y equals 12 would be the appropriate answer in there. So, like, I might have this picture given. I might say solve for y. I would not put negative 12 as one of the options because that would be confusing. Right? And again, in this context, we're just using the positive length. So, any questions on examples 1 or 2? Are those pretty easy? You like those?
I'm kind of confused how you get from the y squared and the 144 to
All right, thank you for asking, Nick. Not a problem at all. What we'll do is we'll show this intermediate step. All right, so to undo a square, in other words, the inverse operation of squaring is square rooting. So I take the square root of both sides. Now, the square root of y squared is the absolute value of y, and the square root of 144 is 12. And what that means for us, when we see absolute value of y equals 12, is that y is some number that's 12 spots away from 0 on the number line. Oops, I did that backwards. So that means that it could either be 12 spots to the right or 12 spots to the left. So y could equal 12 or y could equal negative 12. That's how we solved out that quadratic equation. And then when we brought it back to the context of, oh, I'm dealing with a right triangle here, it would not make sense for me in this case to say, yes, that's right, it's negative 12. That'd be like if I went to my dad and said, hey, cut me a 2x4 negative 12 inches long. He's going to look at me like I'm a crazy person. Okay? But there are other contexts in which negating something like that might make more sense. Okay? Does that answer your question? All right, very good, very good. What did y'all notice was kind of nice about these first 2 examples? Did anything strike you as being kind of convenient? Yeah. Will that always be the case? Sadly not. Hence the need for warm-up questions like what we went through yesterday, where we can take the square root of a number that's not a perfect square, and we can operate upon it without any hiccups. All right, so let's see here. Oh, perfect. There's something I wanted to talk with you guys about. Those previous 2 examples are actually our first of a list of what are called Pythagorean triples. Okay? Look on your screen right here. I've highlighted the first 2 that we looked at. But a Pythagorean triple is simply put a set of 3 integers that fit into the Pythagorean theorem. In other words, 3 squared plus 4 squared will always equal 5 squared. But 4 squared plus 5 squared does not equal 6 squared, and you know, 11 squared plus 12 squared doesn't equal 13 squared. So it's not just any 3 numbers. They are special numbers. Now, I'm not going to make you memorize this list. Say no. No, I'm not. Am I going to encourage you to familiarize yourself with a few of the Pythagorean triples so as to make your life a little bit easier? I absolutely am. I just highlighted 5 of them. Why don't y'all write those 5 down? All right. So the reason that we write those 5 down is not so that I can give you a memorization test. That's not what that is. But it's so that when you're rocking and rolling through a problem and all of a sudden you see a 3 and a 4, you're like, oh man, that's easy. The missing side is a 5, right? Or if I give you the hypotenuse, like 5 and 13, you say, oh, I know, I'm missing a 12 from that Pythagorean triple. Now, I'll be honest with you, I'm not real good at memorizing stuff. So if you have to, you can break down it and look it up. Where I got this list from, let's see if my hyperlink works here. I think it will. Yeah, there we go. Where I got this from, there's a nice little Wikipedia page about it. But you could literally just Google Pythagorean triples and come up with any list that you like. Now, speaking of, while this is pulling up, I'll tell you a quick little tale. Speaking of Pythagorean triples, the Pythagorean theorem, and I don't want to insult y'all's intelligence by saying this, but it's a theorem, okay? And a theorem is something that needs to be proven, okay? The Pythagorean theorem is something that has been proven more than 100 different ways. There are a buttload of proofs for the Pythagorean theorem. There's a little applet running over on the side that you see like a visual proof of it, right? Where a squared plus b squared equals c squared. There's a famous president of the United States that is credited with having his own unique proof of the Pythagorean theorem. Does anybody know that president? Garfield. James A. Garfield. And so there's a ton of websites. The Pythagorean theorem, let's see here. There's one on, so I've got this Wikipedia page pulled up. I didn't have the hyperlink for this, but there's a website called cutthenot.org. I always get confused if it's Grover Cleveland or James A. Garfield.
Garfield's my boy.
Garfield's a cat, bro. Let's see what I did there.
No, he is.
Yeah.
Garfield's pretty sad.
Do we know what Garfield likes to eat? Lasagna.
He does like to eat everything. He's pretty boring cat. He looks like Cat Murphy.
Murphy's not as
You got a fat cat?
We missed out the opportunity to name him Garfield. We named him Murphy.
What's Italian?
And we live on Garfield. So you must Garfield on
Here it is. All right, check this out, fellas. Check this out. Good old James A. Garfield. And what he did was he just reordered the triangle. He duplicated the little in the bottom right there, the bottom triangle. He duplicated it, swung it around, put it up on top, and then he did his by calculating the areas of those 3 triangles, and then also the area of the large shape, which is a which is a trapezoid. And he set those 2 equal to each other, and then worked it out to where it simplified down to a squared plus b squared equals c squared. But anyway, neat little trivia about the Pythagorean theorem, and several of its Pythagorean triples I just copied. These are called the primitive triples. The list goes on infinitely. The numbers just get bigger and bigger and bigger. All right. Now, that being said, we can ask the question, look at example 3, does 7, 9, and then 4 radical 2 constitute a right triangle? So in other words, let's consider the converse of the theorem. Now, obviously, this is not on my list of Pythagorean triples because 4 radical 2 is not an integer, okay? So what we want to do is we want to consider the converse, which says if a squared plus b squared equals c squared, then we have a right triangle. Oh, that was bad. Whose legs are A and B, and whose hypotenuse is C. That's the converse. So what I need to check first is, do these 3 numbers, when I line them up in the equation, do they make a true statement? Okay? Now, I feel as though I must give you a warning. I would be doing you a disservice if I tried to be tricky in this case. Mr. Perry, next year if you're taking help me out, honors geometry thinking, he will be tricky with a question like this. We chatted about this, and I don't want you to get caught off guard. The 3 given numbers do not always represent A, B, and C respectively. Do you know what I mean by that? Do you understand what I'm...
Like 7 is an A.
Yeah. So here's where yesterday's warm-up really comes into play. What does C have to be? And the hypotenuse is what of those 3 numbers? The biggest number. So do yourself a favor and check to see which number is the biggest. Now you might say, well, what in the dump, Coach Morgan, how do I check to see what 4 radical 2 is? I'll teach you. That's why they pay me the big bucks, right? Okay. 4 radical 2, if I wanted to, quote, unsimplify it, square the outside number, square the coefficient, you get 16. 16, multiply that by the radicands, you get 32. So that's the same thing as the square root of 32. If you don't believe me, simplify square root of 32. You'd split it up, square root of 16, square root of 2, and then you think, square root of 16 is 4, and you got 4 square root of 2. Now, the square root of 32 is less than what? Is less than the square root. I was just going to go up to 36. And what's the square root of 36? So the square root of 32 is less than 6. So 4 square root of 2 is not the biggest side, even though it's listed last. Don't fall for that trick. Don't fall for that trick. What should my, quote, C value equal here? 9. My C value should be 9. Oh, that's a dirty trick, you guys. That's a dirty trick, okay? They won't necessarily put them all in order. You have to be clever. You have to be smart. You have to be on your toes. So if I wanted to plug this in appropriately, I would say 7 squared plus 4 radical 2 squared, and I want to check, does this equal 9 squared? That's what I want to check, okay? I'm going to go ahead and tell you, in August, those of you that go and take honors geometry, in August, you will have I think it's a test, but like the first week of school, he's going to give you some type of assessment, and this question will be on there. And those 3 numbers will not be in numerically ascending order. And he'll say, is this a right triangle? And the fool would jump on there and say 7 squared plus 9 squared does not equal 4 squared or 2 squared. Therefore, it's not a right triangle. However, the way I've got it written up in blue, the correct way, square 7, you get 49. Square 4 squared root of 2, and you get what? Thought you alpha dogs would have already had that one worked out. Good, that boy Hogan, 32. And that dadgum equals, last time I checked, 81. So we would say that what? Not a triple. We would say yes, this is a right triangle. Because 4 radical 2 is not an integer. Good question, Will. A Pythagorean triple is defined as 3 integers. In other words, 3 nice numbers that fit into the Pythagorean theorem. A real good practice question for you guys to make sure you understand. Okay? Checking to see whether or not something is a right triangle. Now, oh, go ahead, Luke.
Wait, isn't basically everything Pythagorean? Like, take 5 and 4, it's always going to equal 3. Like, out of 90 and 100, it's always going to.
So good question. What doesn't constitute a Pythagorean triple? Like I used the example a minute ago. 5, 6, 7, for example, is not a Pythagorean triple because 5 squared plus 6 squared does not equal 7 squared.
Oh, so it's whatever, like, if it, like, adds up. Okay, that makes sense.
Correct. Good question. I mean, that's important. And that same question kind of ruminates through my mind sometimes when I'm thinking about these things. It's like, well, does that apply? How broadly does that definition or does that theorem apply? There are certain restrictions on this one to where it doesn't fit. Everything doesn't fit with the Pythagorean theorem. Now, along those lines, literally, fellas, we just got through saying that this doesn't always equal out. Jacob, you okay? Did you fall asleep? This doesn't always equal out. Sometimes c squared will be bigger, and sometimes a squared plus b squared will be bigger. Okay? So what we can do you guys remember we talked about triangles yesterday and the classifications of triangles? How we had a right triangle, but we also had 2 other kinds. Obtuse and acute. And then we had, talking about their sides, we had isosceles, scalene, and equilateral. Good. So y'all are pretty savvy on classifying triangles. Did you know you can use Pythagoras to help you classify a triangle? Right? So like, for example, come out here at a little sidebar. And actually, I don't think, let me scroll down. Okay, good. I was going to say, I don't want to scoop myself here. Let me make up a triangle right here. This, and this. Okay, so a triangle that's obviously, what kind of triangle? And so I've drawn it out to be where it represents an obtuse triangle. So this one we'll say is 5, this one we'll say is 9, and then this one we'll say is 13. So from Luke's comment a moment ago, right? 5 squared plus 9 squared does not necessarily equal 13 squared. Okay, in fact, we know it doesn't because 25 plus 81 does not equal 169. Okay, but it is less than, isn't it? 5 squared plus 9 squared is less than 13 squared. When a squared plus b squared is less than c squared, you have an obtuse triangle. What about if I had, let's say 5, I don't want to do 5. Let's do there, and there. All right, hopefully I've made this drawing obvious. What kind of triangle is this? It's an acute triangle, okay? So let's say this is 10, this is 12, and this is 13, okay? In this case, 10 squared plus 12 squared is more than 13 squared. So when a squared plus b squared is more than c squared, we have an acute triangle. And then, of course, when it's equal to, you've got a right triangle, okay? Now, there's something else to be said about triangles, and I don't know if you guys know this or not. Yesterday, I had to assume that you didn't know anything. You know a little bit more now that we've had yesterday's class, but did you know that there is it's called the triangle inequality, and it says that if you add up any 2 sides of a triangle, they will always be what? Greater than the third side. Not greater than or equal to, but greater than the third side. Let's write that down, that any 2 sides of a triangle when you add them up, not adding up the squares, but actually adding the two sides, they have to be more than that third side. Okay, that's sort of like our checks and balances in the United States government, right? If two sides come together from that three-legged stool, if two sides come together, they can overpower, so to speak, the third side, right? So if I've got 5 plus 9, that's 14. 14 is more than 13, right? 9 and 13 obviously is more than 5, and 13 and 5 is obviously more than 9. Same thing over here. 10 and 12 is more than 13. 12 and 13 is more than 10. 13 and 10 is more than 12. That's called the triangle inequality. Any two sides, the sum of any two sides of any triangle add up to be more than the third side by definition. Okay? So just giving you guys some geometry prep. Now, correct. All right, let's before we get to our word problem, I think that's an absolutely valid point to make here. I couldn't say that. Let me draw it up this way. Oops. Scooch back there. There we go. All right. Triangle ABC. I couldn't say triangle ABC exists such that A equals 10, B equals 12, and C equals 47. You know, that can't be possible because 47 is too long for these other two sides of 10 and 12, right? No matter how I swing the angles around, I'll never be able to reach that. That's too far. So we would have to shorten it up to an appropriate length. And so, well, here's my kind of thought question. This is why I wanted to ask it. I really like how Luke phrased this. If this is, let's say this is 10 and this is 12, there's A, there's B, and there's C. What is the biggest that C could equal? C has to be what? Say it the other way around. You say greater than. C has to be less than 22. Because if C equaled 22, okay, let's play it like that. If C equaled 22, that would be like, check this out. If I took these two and just flattened them down, right, it would be equal to 22. Well, then I can't scooch it up because then I don't have enough room. So that the side here, 22, C would have to be something less than 22 in order for it to make that work, per the triangle inequality. Okay? And I know I'm not your geometry teacher, so I'm not trying to do too much geometry, but these are good things for us to, like common sense things to come into high school knowing. Okay? Now, here's our last example for today, and this one's a good one. It's a word problem application of Pythagoras. Okay? It's a word problem application of Pythagoras. And by the way, check Delta Math tonight for some basic Pythagorean Theorem practice problems, just to get you some practice problems under your belts. All right, the sun casts a shadow from a flagpole. So let me stop right there. I got myself a nice flagpole in the front yard. Anybody have a flagpole at their house? Oh boy, yeah. I ain't talking about like hanging on the side of the mounted on the side of the house. I'm talking about a standalone pole, baby. That's America right there. All right, anyway, we got ourselves a flagpole. There's our flag. Okay. Now the sun is casting a shadow, and it says the height of the flagpole is 3 times the length of its shadow. So our sun must be pretty high up in the sky at this point for the pole to be let's do it this way. Yeah, that's pretty good. So here's my shadow right there. Now there is an assumption built into this problem. I want to see if William Bryan or Nick Pacione, Colton, find me the assumption that they are making about this word problem. You know what I mean by assumption, right? Say it again.
So what they assume you know already?
No, not prior knowledge. That's a good guess. What have I not put on my triangle? No, it's not the length of the sides. Right, you want to take a second guess?
If there's a 90-degree angle between the top of the flagpole and the bottom of the drum.
They are assuming that I know how to install a daggone flagpole. They are assuming that my flagpole is what with the ground? Use a P word. Perpendicular. Or if you're in a physics classroom, you might use the word normal. Or if you were in a physics classroom, you might use the word vertical. Okay? All those words mean the same thing. Perpendicular means makes a right angle with. Okay? So in other words, they are assuming that we can draw a right triangle and therefore use what theorem? That we can use the Pythagorean theorem. The Pythagorean theorem only applies if you have a what? A right triangle. Please don't forget that. I would write that down if I were you. Pythagorean theorem only applies if you've got a right triangle. Now, I've drawn myself out a pretty spiffy little right triangle. Let us see now if I can start labeling the sides of that right triangle, because William Bryan's correct that maybe I know some of the lengths there. It says the distance between the end of the shadow and the top of the flagpole is 20 feet. Is that black, blue, or orange? Good, JT, that's orange. So that's 20. Okay. Find the length of the shadow. So why don't I make that X? And the length of the flagpole. So should I make the length of the flagpole Y? I should not. The word problem has given me a sentence by which I can relate the length of the shadow and the height of the flagpole. Cash, what do you want to do? I've labeled my shadow as X. Read what's in highlighted green and tell me what to relate as far as the height of the flagpole. 3x. Good. 3x it is. Okay. Now, what do I do with that? Very good. Pythagorean theorem for days, son. Pythagorean theorem for days. So I got 3x squared. And I got x squared. And because it's a right triangle, because we are assuming that the pole is upright, we know that's going to equal 20 squared. Okay? Will Perone. That's exactly... that's the right idea, the wrong execution. What's 3x times 3x? 9x squared. Pardon me? I liked the 9. I didn't like the... I think he said 9x maybe. So anyway, this makes what? 10x squared. And we got 400. So divide by 10. X squared equals 40. And so x equals plus or minus 2 square root of 10. Now, which of those would be extraneous? The negative. It wouldn't make sense in the context to say that shadow is negative 2 square root of 10 units long. No. We'd say the length of the shadow is 2 square root of 10 units long. Feet, I guess, is my unit. And the length of the flagpole is 3 times that, so the length of the flagpole would be what? 6 square root of 10 feet long. All right, Luke.
Yeah. Is it just multiplication problem where the exponents would add up? Adding, subtracting.
Correct. It's just multiplication problems.
Also, does it matter that we keep the exponent on the outside parentheses or to add parentheses?
Dude, you are knocking it out of the park with that question. The parentheses are so flippin' important. for the point that Will Perrone made, where he said, hey, are you going to get 3x squared plus 1x squared to equal 4x squared? Why was Will not allowed to say 3x squared plus 1x squared equals 4x squared? What were we actually squaring? We were squaring the whole kit and caboodle here, the whole flagpole, the whole 3x. So it was necessary to have those parentheses in there. Absolutely. And that's a great habit to get into. Okay. I love this problem. It's a good illustration of a simple use of Pythagorean theorem. Okay. So with that, I will cut class off. We've got 2 minutes till the bell rings. Please look on Delta Math tonight for some homework. Okay. And in the meantime, live Jesus in our hearts. All right, fellas. Great way to start your day. Good lesson. I hope you enjoy the rest of your day. Can you go what?